Okay, let's start lecture 11 part 2, integration techniques, more of them. I talked about two different techniques last time, so I will give you two more and go back to the original Robokick program and see how, the things you have learned here can be used. Okay. Techniques, trig functions are so useful, so you can use those functions in many different situations. One of them is this, get rid of the square root. How? Suppose you have those square roots. You set x is equal to a, tangent theta, sine theta, secant theta for those cases. Then what's going to happen is that this squared is a times secant theta, this is a times cosine theta, this is a times tangent theta. Okay. Well, so this is almost much easier than the square root, but you still have this absolute sign. So probably you ask, what can we do about the absolute sign? My answer is the note on the absolute sign is no need. Domain of definition will take care of those. Domain of definition? Yes. Like if you set x is equal to a tangent theta, then what's going to happen is that x, of course, moves from minus infinity to infinity. And for that, the definition, if you remember, theta only varies from minus 1/2 pi to 1/2 pi. Okay? So if you use tangent theta, you have this secant theta here. And for this region, secant theta, that's 1 over cosine. Of course, in this region here, domain here, cosine is positive. So therefore, sine theta is positive. So do you need this one here? No. Pretty much the same way that you don't need those absolute signs as well. All right, so let's take a look at this example here. This is 4 minus x squared square root sitting at the bottom and x sitting at the top. So this is constant minus x squared. So we set x is equal to sine, but since you have 4 here, that's square root of 4 is equal to 2, so 2 sine theta. Then dx, d theta is 2 times cosine theta. Okay. And this one here is 2 cosine theta and absolute sign, you get rid of that. So you have 2 cosine theta in the bottom and the top x, which is 2 sine theta. And this one here, dx, d theta, this one here. So dx is equal to cosine theta plus d theta. Once again, this is the reverse of rule C. From this one here, formally, okay? Formally, what we can do is dx equals to 2 cosine theta d theta. Okay, this is not really true, but you can do that. This is an unofficial, useful rule for engineers. So you substitute that into this dx here, then you get this one here. Aha! Wow. 2 cosine theta cancels out. You have only 2 sine theta d theta. So that's negative 2 cosine theta plus c. And what was cosine theta? If x is equal to 2 sine theta, cosine theta is square root of 4 minus x squared, right? So that's 2 cosine theta. So negative is sitting here, and that's it. Okay. Well, of course, as I've been repeating myself, you can also solve this by setting y is equal to 4 minus x squared. You get square root of y here, and top is here is what? You move this one here, x squared equals to 4 minus y, so x is equal to square root of z, blah, blah, blah. You can do pretty much the same thing here. Okay. Well, I would say this is easy, but anyway, if you're interested in, try that. Okay, the fourth one, use of partial fraction. This is nothing but the power of linearity. What is linearity? If you have linear combination of functions and you differentiate or integrate that, you only need to integrate or differentiate each individual one and make linear combination. So you don't need to differentiate or integrate the big thing, but you only need to integrate or differentiate small thing. That's what this linearity, power of linearity. So direct application of that one is a partial fraction. Idea is break one big fraction to a sum of small fractions, like this one here, x plus a, b over x plus a, or b over x plus a squared, third, cubic power, or cx plus d over x squared plus ax plus b, blah, blah, blah. And you use the following integrals. Integral of this first one is this, and second one to the nth power is this, and that is equal to that. It's not easy, but at least you can use this as a formula, where f and g's can be computed from a, b, c, and d. Okay? Now, this one here, to the nth power, second power, third power, blah, blah, blah. And well, for mathematicians, you have to deal with those, you have to know those. But for engineers, this doesn't happen too often, or I should say, I have never experienced this one here. So therefore, for that, I would say good luck. And I hope that you will not come up with that. All right, example. So how you have a large, well, complicated rational function here. So the approach is to break this one down, partial fraction. So this one here, to do the partial fraction, what you have to do first is to factor the bottom denominator out. Well, you can take x squared out, then you have this one here. So you have x, 1 over x squared, and this one here. I guess that the partial fractions itself, you must have seen before. Okay, so you have 3 terms and integrate 3 separate terms here. Okay. So, and you can leave capital A, capital B, capital C, capital D as is, and you can compute, and afterwards put those numbers in. But let me compute A, B, C, and D by using the common denominator here and compare the numerator. The left-hand side is 2x squared of x plus 4. And this side here for x, a over x, you multiply x times this one here. For x squared b, you multiply this one here. And for cx plus d, you multiply x squared. Okay? And you compute this one out, you get a plus c x cubed, 2a plus b plus d x squared plus 2a plus 2b x plus 2b. And compare the equal power of x. Like x cubed, there's no x cubed over there, so a plus c must be 0, etc. So you got a plus c is equal to 0, 2a plus b plus d is equal to 2, 2a plus 2b is equal to 8, and 2b is equal to 4. From that, it's very easy to find out a is equal to 2, b is equal to 2, c is equal to minus 2, d is equal to minus 4, and you substitute back into that. You get integral of that one, and use those rules, well, formulas, to compute this one here. And I say, go on. Try it yourself. And if you try, well, from here on, it's straightforward, so you can do it. Okay. So as I promised, I will go back to the Robokick once again. So backward approach this time though. From angular acceleration to angle. Why is that? Well, this is angular acceleration. Motor torque first. Long time ago, I told you that the motor torque and angular accelerations are proportional. Why? Newton's law. F is equal to ma. For the rotational case, torque is equal to moment of inertia I times the angular acceleration. So if you have angular acceleration like this one here, this is pretty much the shape of torque history. So you can apply torque here, zero torque here, and some negative torque here. Okay? So we start from angular acceleration. So let's let this is equal to A from 0 to 1, 0, 1 to 2, and B. So this is A, and this is B. Okay? So I am going to start from here. All right. AB appears. Okay, let me get rid of this and that. Okay. So initial conditions. Remember, theta 0 was minus 60 and theta dot 0 was 0. Omega 0 is equal to 0. And the final condition we had was theta 3 is equal to 30 degree for kick, right? And then theta dot of 3 is omega 3 is equal to 0. You have to stop there, right? So I use those conditions, but that's not enough because you remember we used the condition that angle and speed are continuous. Well, not speed are continuous, but the final trajectory we came up with had this property, speed is continuous. Okay, so let me use that. Well, this has to be continuous at any time at all, so at t is equal to 1 and t is equal to 2 as well. All right, let's start from 0 to 1, I'm sorry. Omega dot 1 is equal to A, constant. So you integrate that from 0, starting from 0 to t, that's omega 1t minus omega 1 0. And which is equal to A integrated from 0 to t, so that's AT. So from that equation, this is equal to that, you get omega 1t is equal to AT plus omega 1 0, which is equal to AT. Why? Omega 1 0, the initial speed was 0, all right? Okay, so now we have omega, that means theta 1 dot. So therefore, we can integrate that and to get this one here, omega 1 u, that's a u du, okay? Demi-variable here, okay? I've been repeated myself, right? How important it is to use demi-variable here. So that's going to be 1/2 of AT squared, okay? So theta 1t is equal to this one plus theta 1 0, and theta 1 0 was, yes, negative 60. Okay, so this is what we got. So within 0 to 1, we have both the speed, angular speed, and angle trajectory. So initial conditions and naturally appears. Notice that when we computed that, this one naturally appeared. Okay, and this one naturally appeared. Okay, so by integration, doing this starting from the acceleration, integrating it, you automatically need initial conditions. And initial conditions has to be used to make, to get rid of actually the integration constant c. This integration constant c does not come in here, right? Okay. One initial condition for one integration. That's another thing you noticed, I guess, here. We integrated once, you used one initial condition. You integrated one more time, you use another initial condition. So for each integration, you need a initial condition. Okay. At the same time, we also get theta 1 at 1. You put 1 in here, so 1/2 of a minus 60. And theta 1 of 1, which is a times 1, that's a. Why? Because you need those conditions in the second interval. So second interval, this is equal to 0, so it's very easy that this one here is omega 2t is omega 2 1 plus 0. So that's a. Same speed. And here, this can be used. That's why this is equal to a. Omega 1 was a. And since omega speed has to be continuous, omega 2 of 1 has to be a as well. Alright. How about theta? Once again, we do the same thing and integrate it as, and we have a integrated, so a t minus 1 here. So this one here, it's theta 2 1, theta 1 1, substituted, you get this equation here. Okay? Any questions? So this is a place where we are talking about. Continuity conditions were used. Okay, but more important thing is this. Since this omega 2 and theta 2, we have defined that in this interval. So you can use those expressions only from t is equal to 1. So this integration has to start from 1, not from 0. Because omega 2 cannot be used from 0 to 1. Okay? That's why you needed those continuity conditions at t is equal to 1. And the integration has to start from 1. Okay? It is very easy to make that mistake that you start from, the integration start from 0. So be careful. Be careful. Okay? And, once again, in the next step, we are going to use this continuity condition. So therefore, we compute theta 2 at 2, which is this, and that's it. Omega 2 at 2, which is equal to a, which doesn't change. So that's what you got. All right. So the final interval from 2 to 3, let's do the same thing once again, starting from 2, okay, integration, and omega 3 dot, and omega 3 t minus omega 3 2 is equal to b minus t2. From this one here, omega 3 is blah, 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 and omega 3 2 is equal to omega 2 2, so that you got a here. All right, and integrate this one again. You have this entire thing integrated. You have u, so t squared, and the negative 2b and a integrated. That's t. And here 2. So that's t is equal to 2. T is equal to 2. T divided by 2, that's 2. And this 2. Right? Okay. So, put them together and everything and combine them together and theta 3, 2, put it back, you have this one here. Very complicated equation, but that's what you get. And we also get, why is that? Why do I computing this one and that one? Because in the original problem, we were given not only the initial condition, but also the final condition. Theta 3 of 3 was 30 degrees, and theta dot 3 of 3, or omega 3 is equal to 0. Okay, those were the two conditions. So let's use that. Theta 3 of 3 and omega 3 of 3. So you have two equations and two A's and B's. Okay. From that, A is equal to 45, B is equal to negative 45, easy to to compute that. So this is what we got. Omega 1 is 45t and 45 minus 45t minus 3. And theta 1 is this, theta 2 is equal to that, or either this way or that way. This way it says that t minus 1s are t is equal to 1, this one disappears. And this way t is equal to 2, this one disappears, whatever you like. And theta 3 is this. But if you take this one out, then you have t minus 3 squared plus 30. This one is easier to use, right? To see what's going on. When t is equal to 3, this part becomes 0, so only 30 remains. That's the final condition. All right. Identical to the former result. Yes. I don't think you remember the former results we have gotten long time ago, but those are the ones we have gotten. Okay. The graph. Comments. And this one here. Old approach started from the angle trajectory and went to the acceleration. The new approach is from motor torque first and then goes to that theta trajectory. Advantage of the old approach is the easy to visualize the motion because you see this one first, so you know how the angle changes. The advantage of new approach is easy to control the motor. After all, what you need to do is to program the control of your motor. So that's where you start. So it's easier for controlling the motor. What are the requirements? Here, requirement of smoothness of trajectory, and that really assures that the speed is continuous. Here, requirement is initial conditions. Initial conditions and the final conditions and continuity, blah, blah, blah. Those are the ones. So tools, here, this is differentiation. You differentiate to get this one here. Of course, this is integration from here, there. And to get rid of the integration constant, those initial conditions and continuity conditions are necessary. Okay. Use one or another, case by case. It all depends on what you want to do in what situation here. Sometimes you may want to do the old style, or sometimes you may want to do the new style. But now you can do both of them, right? Because you do know the tools. You can use the tools to go one way or the other. Okay. So, the conclusion is that the calculus is a useful tool for robot control. Okay, that is the end of this lecture. And next time we will go into more applications of differentiation. Differentiation is such a useful tool. There are so many different applications which are useful for robot control. So I'll talk about that next time.